Okay, should I get started finally? Yeah, all right. So the last time we talked about time integration, explicit Euler. I think I ended. Oh yeah, this is what I ended with. So let me restart with that. This was a toy example demonstrating the explosions of explicit Euler. So explosions are an informal term for instability, meaning that the solution is not even approximately correct. The solution, there is an error accumulating at every time step, and it's accumulating over and over again. Or maybe better said, so let's take a look at it. The explosion happens when the step h is 1. H is the time step, so this is the time step, the t for a matter. And here is just one dimension of our ordinary differential equation we're trying to solve. And what happens in explicit Euler is that it overshoots, right? The right solution is this, the black curve. So we are solving this ODE. I'm going faster because we had it. I'm just recapping that, okay? We are solving this ODE. So we're looking for a function whose derivative is minus 2.3, the function itself, okay? This is a toy case, so we know what the perfect solution is. It's e to minus 2.3 t. So that's this black curve here. And what explicit Euler does, it overshoots, because with h equal 1, the time step is too large, so it overshoots. The right solution at 1, so here is 1. The right solution should be here. Explicit Euler overshot here, right? If we took a smaller time step, we would have been much better off, right? Because then if we went like here, then it would be much more accurate, right? What happened? It overshoot, and what it wants to fix the overshoot by another overshoot. You can imagine if we are looking at a spring, the spring got overstretched. It's not happy, right? It creates large forces to contract, and what happens again? It overshoots even more. As a solution, it creates even larger forces, right? It's sort of like escalation, like in a war, right? Like somebody punches you a little bit, somebody punches you like harder back, and at the end there is a disaster. So that's exactly what explicit Euler does. And I think what I ended with was computing the region of stability. So it can be stable if your time step is small enough. Okay, so all here for h equal 0.7 and lower, I think the threshold is something like 0.87, right? That's what we ended with computing. So below that, it's stable. So that's slightly disappointing. That means you have to worry about this. And today, I would like to talk about how can we do better than this. How can we essentially do better at time integration? So the most obvious thing is already here, right? That means to decrease the time step h. So the smaller time step you do, the more stable it will be. That's the simplest possibility, and it's not crazy depending on your application, but you will have to pay for it, right? Because you typically, this is an important thing to note, you typically want to simulate the real time, right? Like what people typically do when they implement it for the first time, even more experienced people, they just display the result of every single step, right? But if your time step is like 10 to minus 6 seconds, which is where explicit Euler would be pretty stable, then you would be rendering a really slow motion video, right? So you probably want to be rendering it. Well, what frame rate do you want to be rendering things? What time step would you ideally be taking in graphics?
Well, something better than 24 frames per second.
Exactly. So no, 24. If your display has 60 frames per second, right? Then that's what you want to be using, right? Or games typically run in 30 frames per second on a good day. So that would be your ideal time step, right? 30. So that would be like 30 milliseconds, 0.033 seconds, right? Which is pretty huge time step for explicit Euler in physics. You'll try it, you will play with it for your next homework. You will see that it explodes very quickly. So you need to do something. So you can decrease the time step. So that means if you want to be rendering a frame every 33 milliseconds, when you're simulating some world, and in the world you have some simulated time, right? And every 33 milliseconds of that simulated time, you want to render a frame. So you can just say that you will do 10 steps of explicit Euler within one step, right? So you can do that, and you will get more stable result. But that means that you actually have to do 10 times more work, right? all the computations, probably the bottleneck will be the computations of the forces here. It's not terrible, but the cost will go up. It's not crazy if you are doing it on some GPU or something highly parallel, because you can easily, trivially parallelize all these computations. So in that case, it makes sense, or can be justified in some cases. So there are better ways, and that's what we'll talk about today. So one better way is to use a higher order method. Let's first do higher order explicit methods, and then we will switch to implicit methods. So basically, the idea of explicit Euler was to truncate the Taylor expansion here, right? Just use the first derivative as an approximation of the function. Well, of course, we can use a more accurate Taylor expansion, right? We can only truncate it here. So we can try to use second order approximation and see what we get, right? So let's take a look at that. So we truncate it here. So here, the remaining terms, I can also write it like OH cubed here, right? Now, we have a little bit of a problem here because we only know the y prime, right? Why do we know y prime? Because that's the problem, the ODE, that's the instance of the problem, right? In our case, what is the y prime? Just to push. There is velocity, and another component there is, if you remember from the last lecture, there's the force, right? Velocity is the easy part, and the forced computations, that's the harder part. So we have a function to compute y prime, right? If you read the Baraff and Witkin course notes, which is one of the recommended readings, then they recommend you to structure your code to have a generic ODE routine where you just pass it a function y and a derivative of the function, and it just does the integration for you. So the routine doesn't even know that it's integrating forces. It's sort of like an abstraction, like a good, or in other words, good programming. Okay, the second derivative of y, we don't know. We don't have any function computing that. So what we are going to do, we're going to use a finite difference approximation, and this will lead us to Heun's method. So let's do this. So if you don't know the second derivative, we can do this. We can do the forward difference approximation. Assume you know this, and we are making some OH error here. And if we plug this in here, let me try to compute it quickly so you trust me. So what I'm going to do, I'm plug this finite difference in here. So I will get that y t plus h. I will say that's equal. I will say it's equal. And I will put there this. So I will get this I will just copy. So h y prime t. Can you see that? Sort of. Plus, and what I have here, so here is h squared divided by 2 divided by h, so it will be h over 2, and then I will have this, y prime t plus h minus y prime y derivative t, okay? And this OH gets multiplied by the h squared, so this is h squared or half OH, that's this OH, plus the original OH cubed, okay? Did I do some mistake?
Yeah, this second derivative estimate is biased to the right, right? In the sense that we're using...
That's correct, yes. I will, in a little bit, I will show another method which uses central differences and that doesn't have that problem. But it doesn't matter, it's biased to the right. The error is still OH, right? So I'm just trying, what I'm trying to derive here is the Heun's method, which is a second order accurate method. So one order accuracy higher than Taylor. So even though it's biased to the right, which this forward or backward differences always are, the order of accuracy will be higher than of explicit Euler. Okay? Okay, let me finish this real quick. So I just need to rearrange it nicely. So the yt is here, right? And then what I have here, so here I have h y prime, and there's minus h half. So that gives me, if I'm computing right, h half y prime t, right? Plus, and this is also h half. This is y prime t plus h here. Okay, and this whole thing I can just write as OH cubed because this is h squared times OH. And all together, that's the beauty of the big O notation, right? I can just lump it under one big O thing. And this is what I wanted to get here. Yeah, that's correct. So the neat thing is that the update rule, and here I already computed for you the order. The update rule essentially blends the first derivative at y and the first derivative at, the first derivative at t and the first derivative at t plus h. Because, what I mean by blend, you can also look at this as like this, right? As h, and then do 1/2 of this plus 1/2 of that. Okay, that's what I mean by the blend or average. Okay. So that's the update rule. There is still a small problem with that. So this is the update rule I derived before. The small problem there is that I don't know y prime at t plus h, right? Because the y is that's what I'm computing, so I don't know that yet. So what we are gonna do instead, we are gonna use the Euler step to estimate it. And it turns out that the estimate has sufficient accuracy to get second order accuracy at the end. So what we are gonna do, we're just gonna take the approximate derivative at our current step, the n yn. I will step forward, we'll get some yn plus 1. And that's where we estimate the y prime. So this yn plus 1 prime will be our estimate for y prime t plus h, or this will be. So ultimately the update rule for the Heaven's method looks like this. It first does the Euler step forward. It probably will be easier to illustrate it visually. Oh, let's look at the formula first. So this is an Euler step which goes forward and gets you like a first estimate on the slope. And then what we do, that's an interesting thing, then we essentially blend between the slope that dictates us f and the new one, this one. And then we take a step with this slope, with this derivative. Okay, this might be confusing. Let me try to explain it visually on this slide. So first, we do the standard Euler step. Okay, so we are here. Here we have our current value. It could be the initial condition if that's where we started. We compute the slope here, so that's f, t, and yn. Okay, that's this blue thing. And when we take the step, okay, then we look at the slope here, the value, that's the derivative of the function here. That's the f function, right? So that's the tn plus 1 y tilde n plus 1. That's where we got by the Euler step. And there is some slope. That's this. And then we bring it back. That's this, and we average it. Okay, with the original slope. So this is the averaged one, and with the averaged one we take the full step, and that's our result here. So here you can also nicely intuitively see why this is a better idea than explicit Euler, right? Because explicit Euler would be shooting right here, and this essentially gets a better estimate of the actual function we are trying to compute and gets a more accurate result. And if you look into the math carefully, then you find out that this is a second order accurate thing. I guess I already started it, right? Because you have here, because you basically estimate the second derivative here, and you are only making error OH cubed, so that means you have a second order accurate method. And that's called the Heaven's method. And if it bothers you aesthetically, like it bothered Valentin, that this is biased to the right, because finite differences, forward and backward finite differences always are biased one way or the other, then you're of course not alone. There is a method that addresses exactly this issue. You know, it turns out it's basically just aesthetics, because ultimately also get second order accuracy. So that's the explicit midpoint method. So here the idea is essentially the idea of central differences. So the trick is that if you want to estimate the derivative using finite differences, if you estimate it halfway through, so meaning if you have samples at t and t plus, let me draw that, it will be clearer. So if I have a sampled function, here is some y t, here is some y t plus h. So you know the values of the function here and here. And it turns out that if you want to estimate the derivative here, y prime t plus h half, you will get a higher accuracy. You will get second order accuracy, even though you are using basically the same formula. Do you want to know why that? Why is that? It's when I say it like this, it looks like magic, but it's sort of easy to see that from Taylor expansion. That's how all these higher order integrators, by the way, are derived. You just write the Taylor expansion and you massage it, and the higher order terms cancel out. So let me write some hard math. It's a little bit easier if I do it like this. If I look at the Taylor expansion of y t plus h half, and here I will write y t plus, oh sorry, I meant t minus h half, and from the two I would like to extract formula to approximate the derivative at t. This will make it more symmetric. I could do it like this, but the formulas would be a little bit more messy. So let's do Taylor expansion for this. So that's yt plus h half y prime t, of course. What is the next term? H squared divided by something. What is that something? I'm just doing Taylor expansion. 8, correct. Why? Because I have h divided by 2 squared and 1 divided by 2 from the Taylor expansion, right? It's 1 over n factorial, if you remember your Taylor thing, which you probably do better than I do because you had it more recently. And some error on the order of h cubed, okay? So now I do the same Taylor expansion here. So here I'll get minus, right? Minus h half y prime t. Here the minuses will cancel, so this is just this. Plus, again, some error. And now look what I can do here. I can do this. I can take this value, t minus h half. Actually, no, let me take this one and subtract t minus h half. That's correct. And what I will get, see, I take this one and I subtract this one, okay? And what I will get is an interesting thing. I will get h times y prime t, because this term canceled out and this term also canceled out, okay? And this is why we get the higher order accuracy plus some OH cubed term, okay? So this is why from central differences we get 1 order more accuracy than from forward or backward differences, because there is this funny cancellation that just cancels the higher order term. This will come back again in fluids where, so I guess you can forget the mathematics. You will certainly forget the mathematics at some point. But what I want you to remember is if I have a sample here and sample here, if you want to estimate the derivative here or here, you will be making higher error than if you estimate it halfway through. Okay. This will come again in fluids when we will be talking about the MAC grade, where the discretization structure is actually designed exactly to take advantage of this fortuitous cancellation, which gives you higher order accuracy. Any question? Yeah?
I'm trying to understand what it means to say some order accuracy. Like if you say third order accuracy, what does that mean?
Oh yeah, so that basically means that means that what is hiding in this O, right? So if the Taylor expansion is exact if I go to infinity, okay? To going to infinity, I would have to do infinite calculations there, so I don't want to do that. So I truncate it at some point, right? And the point where I truncate it, that's essentially the order. And what does it mean in practice? It means that your h is something small, right? And as we discussed, sometimes it's not small enough, so you need to make it smaller and smaller, right? So of course, if h is small, then h squared is very small, and h cubed is super small, and so on, right? So that's the intuitive idea why you actually care about a higher order integrator, right? I guess that's a good point. I should have pointed it out already here at Howen's method. The fact that you have a second order accurate integrator that's only making an error of OH cubed, there's one h because you are multiplying by the time step, so the error is OH cubed actually. That's actually great, right? Because if you wanted to reduce the error just by making the time step smaller, you would end up probably doing much more work, right? Like imagine your h is 10 to minus 2. If your error by doing a more higher order accurate scheme is squared, so that means your error will be only 10 to minus 4, right? Imagine you had to subdivide it 100 times. Well, that would probably be much more computation, right? So that's why we care about the higher order integrators. You will see that when you will play with the next homework, where you will get to test this.
But it's also how large your error gets relative to your time step calculation. So it's kind of a ratio too, right? I mean, it's not a ratio, but it's a, yeah, I don't know how to.
Yeah, that's sort of I mean. Yeah, the error is we are always here talking about local error, and that's with respect to your time step h, right? And that's you're right. That's basically how the error scales with your time step.
So I'm still wondering if the original problem was that if h is too high, then overshoot is high. Does this method fix that to some extent?
It doesn't fix that, but it mitigates the problem considerably. Okay. So maybe I could have computed it here. If you used a higher order method, maybe you could get away with time step 1 here, right? I mean, this is such a simple example that it doesn't matter that much, but yep, makes sense. Okay. So where are we? The midpoint method. So the midpoint method takes advantage of this fortuitous cancellation of central differences, and also it's also more aesthetic, right? It's not biased to the left or to the right. It's symmetric, which is beautiful. So what it does, it does an interesting thing. If we take an Euler step halfway for half of our time step for h half, we will get the y tilde n plus 1 half. And then we just use the slope evaluated at that point to do a full Euler step. So similar, you could imagine similar sort of picture as before, except that now we are stepping on the half step forward, and use the derivative estimate to do the full step. So if you think about it, all these methods. Let me first, I guess, go over the Runge-Kutta 4. I guess the Runge-Kutta 4 is the most well-known one. That essentially extends this idea even higher. Okay, so explicit Euler could be seen like a first order explicit method. The Hohen and midpoint could be seen as second order. The RK4 Runge-Kutta 4 is a fourth order accurate method. So, but it's essentially an extension of the same idea. I'm not going to derive that properly. You can see it's a little bit more complicated, but it's essentially a variation on the same idea. So first we evaluate the slope where we currently are. We take a half step with it, evaluate the slope again. Then we do a half step with the new slope. Then we do a full step with the K3 slope, and at the end we take a weighted average of all of them and do a full step with this average. And the way this scheme is derived is that all the higher order derivative terms cancel out, and you have it accurately up to order 4. So this is a popular integrator. I guess maybe I can show also the visual picture, even though I don't want to spend too much time on that because of reasons I will explain shortly. So I think it goes something like this. So again, starts where you are, compute the estimate of the derivative, do a half step here, compute your slope, K2 here. Now the K2 is used for a full step. What happens? No, with the K2 we also do half step. Yeah, with the K2 we do half step. That's how we get K3. That's this thing. So it looks like magic. You can probably derive it from just by massaging the Taylor expansion. And with the K3, with the K3 you do a full step, and eventually you do a weighted average of all these guys, and then you shoot somewhere which is pretty close to where the actual function is. So, and you can keep going to get even higher accuracy, right? The higher you can see that what you are paying with, you do more evaluations of the function, right? So in your case, the bottleneck would be evaluating all the forces according to Hooke's law, which is small amount of computation, but there's some computation, right? There will be some divides by some square roots and so on, some memory operations. So it's not totally for free. Because the memory will probably be slowing you down most, and you'll be reading the endpoints of the particles there. So here you have to do 4 evaluations of the function. So basically the idea is that you do more evaluations of the function, and you get a higher order accurate method. So essentially, you can think about it as sort of trying to do a more accurate estimate of how the function varies on this interval, or like a smarter way than just doing subdivision, right? Like lowering the time step would be equivalent to just subdividing and doing lots of small steps. So this is a little bit smarter version of that, essentially, of these higher order integrators. This RK4 is what we were originally using in the Jolo cube demo. This time we changed it for the next homework. So I don't think we want to be doing this. Well, maybe we'll still keep it there. I'll see. So to wrap up the explicit integrators, it gets much better if you do higher order integrators. It gets much more stable, but the explosions will still be there. They just won't go away. And again, it depends on what you are simulating, but typically in physics-based simulation, especially if you are doing something like games, the external forces can be pretty insane you are exerting on the system. You know, like if you have a character running in a game, running around, the character needs to respond immediately to user control, right? It needs to like turn on the spot. Or if you are shooting something, the user wants immediate response, right? Which means that the physics is actually dealing with pretty insane forces there. So the explicit integrators are essentially not very useful, because for high forces, they will almost always explode, even the higher order ones, in the applications like we want to use it for, like this physics-based simulation in games or for movies. It of course depends on what you are simulating. If you are not pushing it too much and you don't have too stiff springs, you don't have too high spring stiffnesses there, it might work just fine. So I guess this is summarized on this line. This is what we mean by stiff problems. And people realized this in graphics quite a while ago. You will realize it the latest when playing with your next homework, because it's sort of frustrating when it all blows up. There are some strategies you can do. I have seen like in MATLAB when we were playing with something a long time ago. You can do adaptive time stepping. Like if you can sort of try to detect if things start blowing up, and when they start, you can be lowering the time step. But it's actually very, I played with some simulator was doing exactly this. It's very annoying because when things go wrong, then it's lowering the time step, which means it will get even slower. And then usually it doesn't really help, so it has to make the time step even smaller, so it's actually slowing you down. It's very frustrating. And eventually my test still, it can slow down, so it won't be making any progress actually.
It's like Matrix mode.
What do you mean?
The movie The Matrix.
Oh, yeah.
You know, when he starts firing stuff and everything slows down.
Yeah. And that happens exactly when the simulation is about to do something interesting, right? Like when you're like simulating like piece of cloth and now you pull it, right? That's the thing, I guess, in effects, you want to do something dramatic, right? Like you're like shooting something, right? And exactly these interesting cases, that's exactly where the problems happen. The best case is when nothing is moving. Then you can do very large time steps, everything is cool. Okay? But we are interested in the hard cases, when we are really pushing hard forces and we have stiff springs. Why do stiff springs matter? Again, if you have something very mushy, then it sort of doesn't matter that you applied hard forces to it, because it's so compliant, it will just stretch indefinitely, right? Again, not very interesting, right? So this is called stiff problems, and that's the typical problem we have to deal with in physics-based simulation. I guess it's like an informal term. And the problem with explicit time integration is that you don't really know how small time step you need to be taken. So you will probably end up taking conservatively small time step. So if you want to do better than that, you need to use implicit time integration techniques, and that's what I will talk about next. Implicit techniques are really popular in graphics because they are much more stable. They don't have these explosion problems pretty much at all. Pretty much. So the most basic but already very good implicit technique is Implicit Euler, and it's a cool idea. So remember, explicit Euler, what did it? We were at some state yn at time tn. We computed the slope and we stepped forward, right? That's what explicit Euler was, right? Implicit Euler is interesting. It actually says, so it says that we actually evaluate the derivative at Zn plus 1. That's the step where, that's where we want to step. That's the solution, essentially. So let's see if I can explain it better using this picture. So if we are here, if this is the t and yn, explicit Euler just, that's why it's called explicit, by the way. It just computes the slope here and takes a step there, okay? What implicit Euler says, it says, I want to find the solution of after one time step, such that the time step essentially is what I would get with the slope at the end of the time step, okay? The other way you can look at it, and that's also sort of cool, the other name it's also called backward Euler. Backward Euler means the same as implicit Euler. Those are just two names for the same thing. And the backward alludes to the fact that it's actually explicit Euler going backward in time. If you started at Tn plus 1 and Zn plus 1, if you started here and you took a step back in time, minus h, you would arrive where you were. Okay? So that's another way you can understand the implicit Euler. It's going there, it's going to such a point that if you took a step back in time, you would arrive where you started. This is what this means. Okay? So at first look, it looks sort of insane because what you are trading off an explicit formula. Explicit Euler, there is an explicit formula how to compute the solution in the next step. Okay? In implicit Euler, I trade this off for a system of equations which even for mass springs are nonlinear. Okay? So to solve the implicit Euler, I need to solve for Zn plus 1. I need to solve this. In general, this is going to be a system of nonlinear equations, and I need to solve it. And the Zn plus 1 is going to be my solution. Then I can make another step. Okay. So at first, it looks like a very bad trade-off because this is, of course, much more complicated, right? Here we'll be actually solving a system of nonlinear equations. But it turns out that this really pays off because the resulting technique is way more stable. Maybe you can try to think intuitively, why is it so much more stable than explicit Euler? It's just an intuition.
Because when you march back in time, you know that your system is not going to explode.
Exactly, because it was not exploding before, right? That's the beauty of it. The explicit Euler, if it sees some huge forces, like some spring stretched really a lot, huge forces acting on it, well, the explicit Euler just goes with them, right? And maybe then will be even huger forces and so on. Bad things happen, right? And just as you said, this cannot do it, right? At the step back in time, it needs to be sane, or in other words, it cannot step forward to an insane configuration to overshoot. It actually turns out that this has the opposite problem, that it's too conservative. It actually introduces artificial damping. But that's a second order effect, which we'll discuss later. So first, let's take a look how implicit Euler works on the test equation. So this was our toy problem to test a numerical time integration. So we are just solving this dead simple 1D ODE, one-dimensional ODE. And this is what we did before. This is what we got for the explicit Euler, and from this I derived the condition for stability, right? Because if the explicit Euler is to be stable, then I need to have 1 plus h lambda to be less than 1, right? From this we computed that it was 0.87 or something like that. That was the threshold where explicit Euler becomes unstable. So let's take a look what happens with implicit Euler. So this, if I take this away, this is the formula for implicit Euler. So instead, so the slope is not yn, but it's yn plus 1. That's the only difference here. Okay. So if I do this, let's see, yn plus 1. So I put it on the other side. So this will be 1 minus h lambda equals yn, right? So that means that yn is 1 minus h lambda. What am I doing? I'm doing a mess. I meant yn plus 1. Sorry. Yn plus 1 equals y minus h lambda inverse yn. That's what is here. Okay? So that's the step of implicit Euler. It's sort of cool because on this simple test equation we can actually really see it and really compare it, right? So if we can resolve the recursion, if we are starting at some y0, if we are just multiplying by this factor here, y minus h lambda inverse, okay? And if we multiply n times, we will raise it to the power of n. So this will be stable if and only if this thing in absolute value is less than 1, right? Something we are multiplying over and over again, so the absolute value of that better be less than 1, right? If it's to be stable. And it turns out this is actually cool. If your h is positive, and we assume here that the lambda is negative, that the solution is this attenuating curve. So lambda we assumed is negative, h is positive. So this is something greater than 1. So altogether, the absolute value is 1 over something that's greater than 1. Well, that's something that's less than 1. That means this is always stable. No matter the time step. You can take time step a million years, will still be stable. For this simple test equation. It turns out that for linear elasticity, implicit Euler is also always stable. For nonlinear things like mass springs, I'm not sure if you can prove that it's always stable. I honestly don't know, but I don't think we have ever seen it to explode. There are some other problems which have to do how do you actually solve the system of linear equation or nonlinear equation, which is what we'll get to. So here is a comparison of explicit versus implicit Euler. So again, explicit means that the quantities are known and we have explicit closed form formula, right? Directly compute the solution. Here it's implicit because you have to solve for it by solving a system of nonlinear equations. That's why it's called implicit Euler, or backward, which alludes to the fact that it's sort of going backward in time. So why the formula, why the equations are nonlinear? Well, already for our mass spring system in 3D or in 2D, in 1D it actually still be linear, but in 1D it's not super interesting because there's not that much you can simulate in 1D. Already in 3D you get nonlinearities, right? And what's even worse, as I said before, it's non-convex. The moment you have at least two springs attached together through a mass point, it's also non-convex. The potential is non-convex. Which is what actually complicates things. So that, the fact that it's nonlinear, that's obvious, right? That basically there is a reciprocal square root. So of course it's nonlinear. Actually, here is one thing maybe we can say already now. It will be more important in continuum mechanics and finite elements. The Hooke's law is a linear material law. The nonlinearity is the geometric nonlinearity. It's exactly the type of nonlinearity we have seen with rotations. That's why we need to do these tricks with quaternions and worry about slurps and so on. It's because rotations are nonlinear. That's the I guess the essential problem of the geometry of the real world, and at least the geometry we use to approximate the real world. That's this nonlinearity due to rotation. So in the case of springs, it means that the spring can rotate in space arbitrarily without changing its potential energy, of course, right? And that in math we have to account for it by normalizing the spring direction, and that's what leads to the nonlinearities. Okay, so how do we solve the system of nonlinear equations? How do we actually solve implicit Euler? Do you know it? The answer? Like I said it before.
Graphically?
Graphically?
Graphically or substitution?
What means graphically?
Well, you can plot given a quadrant and you can plot and see the intersection points.
That's a good idea. That's a good starting point of an idea. Except that eventually you have a mass spring system which has like 10,000 degrees of freedom, right? So at that point, visualization becomes actually its own field, right? Scientific visualization. But you have the right idea because this. Oh, you know what? Let's do it this way. This is the right idea. Let's do it this way. So let's see. So I have some function. So let's see what sort of function. Because this function would be good. Function like this, okay. And I need to find its root, where the function touches 0. Okay, this is some general nonlinear function. I guess I can start. Okay, it's called Newton's method. I can give this away. So the system of nonlinear equations can be trivially rearranged to a nonlinear equation equals 0, right? So it can be rearranged that we are looking for 0 crossing. We basically just substitute. We just take this and put it on the other side. So we are looking for 0 crossing of some nonlinear function. A nonlinear function, you can do anything, so this is nothing that special. So how do we how do we find 0 crossing? Well, we start with some initial guess somewhere. Okay, so let's say this is my initial guess. What do you use as an initial guess in physics-based simulation typically?
Tangent line.
No. Where do you that's going to be the next step, but the first where do you start? You have to have some initial guess of the solution.
Solution the previous time.
Exactly. Because if we are integrating forward in time, right, then we have either we just started, so we have the initial conditions, or we have the frame we just computed before. So that's going to be our initial guess. So that's here. And then exactly as you said, how do we move from here to find this? How do we find where this function hits 0? At what point x? So this is some function f, right? This is some x. This is f of x. We're looking for the point x where the function hits 0. Well, what are we gonna do? That's the idea of Newton's method. We are gonna compute the tangent here. So in other words, we are gonna form a linear approximation of the function f at this point. How are we gonna do that? Derivative, yeah, exactly. It's just the derivative of the function. If it's a multivariate function, it's the Jacobian or the gradient, right? So that's why we were working so much on multivariate calculus, because that's exactly what's needed here, as you will see in a second. So we essentially compute a linear or affine. Well, correct is affine approximation because it doesn't pass through 0. There is some offset here. So affine approximation of the function, and we intersect the affine approximation with 0, and we get this point. Okay. What are we gonna do here? Well, we're gonna look what is the value of the function at this point, and we do the same thing again, right? We do again affine approximation, best fit affine approximation. We get somewhere here. And as you can see in this nice case like this converges very fast. That's the beautiful feature of Newton's method, and gets you to the solution in good cases very quickly. So I guess if you want to put it in some math, here is some math on this. So this is so we are looking for roots of function g, which is a general nonlinear function here. We start with some initial guess, which would be typically the solution of our previous time step. There are actually some better things you can do, which maybe we can talk about later. Some better initial guesses you can imagine. Or I can give it away already. A better initial guess typically is, you know what? Newton's first law. When you say there are no forces acting on it, the stuff is just moving forward in time with the velocities it had. That's another initial guess which we actually found that sometimes works really well. Anyway, but it's just a guess, right? Even though the guess actually is important for reasons I'll explain later. So then we establish the affine approximation. So that's again Taylor expansion, always the same story. So here in 1D this is the derivative times the displacement. In multivariate things this would be the gradient and this would be the dot product. Okay, and this delta y is the displacement we are solving for. Okay. So the picture is, if we are here is our starting initial guess. We are looking for the step we need to take so we get to a better approximation of the solution. So that's this delta y. I guess I could put it here. This is the delta y. This is the step we want to take. We discard the higher order terms, and from this we can solve for delta y, right? So again, in the multivariate case, this would be actually solving a system of linear equations. I'll discuss it in more detail in a little bit. In the 1D case, it's just division. In the 1D case, it's easy. And then you need to iterate this, right? Just like on that picture. I guess I have a better picture of that here. Newton's method, very, very important method in numerical mathematics. So here's the same picture again. So here we started. We do the optimal affine fit. We intersect it with 0. We find that's in the next iterate, and we continue. We iterate. Okay. There are several flavors of Newton's method. This is the Newton's method applied to solving a system of nonlinear equations. You might also know Newton's method from optimization, where it's used to minimize a function. It's still the same idea. There are more like different formulations of the same idea. I guess the optimization point of view is cool, and I will probably explain that later why it's important that led us to get even better integrator than this Newton's method. Okay, I don't want to go too much on a tangent. Let me just mention this. In the optimization case, if your function is convex, then Newton's method converges extremely fast. Almost always in like 20 iterations is the maximum, and you are done. And in the convex case, it doesn't even matter where you started. Unfortunately, here we don't have the convex case because I showed you the counterexample why the potential of already 2 springs cannot be convex. So here it gets tricky, and that's also why the initial guess matters here. So there are in the non-convex cases there are some problems with Newton. So here is one problem that can happen. So imagine you started here. This was our initial guess. We established the affine approximation. This is the function, right? We are looking for the 0 crossing here. Established the affine approximation. We found this point. Then we do next iteration, and brings us exactly back. So then we be cycling forever, right? Not very good. So the solution to that is to do line search, and basically, so do careful steps along this line, because here what certainly happen is that you overshoot, right? So you don't want to do that. You would ideally want to stop the line search here. I think it makes a little more sense to explain it in the context of optimization. We are actually minimizing a function as opposed to looking for roots. I'm not sure, maybe you can do line search in this case to look at some residual or something. In physics, people usually don't do this. I'll explain why later. There is another problem that can happen. In the general non-convex case, you can have these problems. You can hit a point during the iteration where the gradient is 0, but it's just a local optimum. It's not actual 0 crossing, which would be somewhere else. That's a potential problem. Again, we typically don't do anything about that in physics-based simulation. So this is the conclusion of this. It's an iterative method, which is very powerful if it works, but it doesn't have to work always in the non-convex case. Okay, but fortunately there are ways to make it work. One famous way is due to Baraff and Witkin, Pixar guys from 1998. I think Pixar is actually still using their cloth simulator, which is essentially based on this paper. It's very, very, very famous paper. So here is the main idea. They call it semi-implicit integration because they essentially do just one step of Newton's method. That turned out to be already like infinitely better than the explicit integration method. But that gave them very stable integrator. Here is how the Baraff and Witkin's method proceeds. It's really just one step of Newton's method, but we can write it down exactly for the equations of motion. So, yep.
Was the Newton's method for solving linear systems or nonlinear systems?
Nonlinear systems. So the way it works, Newton's method uses a solver for linear systems as a subroutine. You iterate a solve of linear systems to solve the nonlinear system. And that's because how it works by successive linearization, right? It finds this affine approximation, which works only in small neighborhood. So then it takes some potentially small step, right? That's by the way, good that you mentioned it. That's a way how you could fix this problem, right? Here you were, or Newton was too greedy and took too large of a step, right? And that's why is that a problem? Because our affine approximation is guaranteed to be accurate only in some small neighborhood, right? Actually, only in infinitesimally small neighborhood, which is sort of ugly, right? So in infinitely small neighborhood, it's very accurate. So the easiest solution would be to limit the time step, right? Limit the step and do more iterations of Newton. Pay the cost of compute and get the right solution. Yep.
I'm trying to remember the first part where you introduced that implicit equation stuff. It was probably stable for any values of h or something like that.
Yeah. So how it's stable? That's a good question. So you can prove that for linear forces it is stable. Now already for mass, it's sort of funny because already for mass spring system the forces are nonlinear. There are some cases where you do linear elasticity even in graphics, like when you are like simulating a bridge or something and it's only shaking just a little bit, it's not doing some crazy motion around, then you can use linear elasticity. Or like in material science, I think they use it a bunch. If things are not moving too far, then you can just use linear elasticity. I think in that case, you can prove that the implicit Euler is unconditionally stable. In the nonlinear cases, I am not sure honestly, but you will probably not be able to get it to explode. We put it that way.
That's what I was.
The only problems could be the problems that you might encounter. They would typically be from not solving the system of nonlinear equations exactly. Right? So the problems typically come from the problems of Newton's method, like something like this, right? Or finding some weird saddle points, critical points which are neither local minima or local maxima. Okay, any other questions? No? Shall we look at Baraff and Witkin's method? Would be good to finish this. So we write the equations of motion. So here we write it fully, no shortcuts. So this is the mass matrix, these are the forces, and it's note that this is implicit, that the velocities are evaluated at ti plus h, so ti is the time step where we currently are, and plus h is the next one. And the forces are also evaluated at the time step we are computing, not the one where we currently are. We are at ti, and we are computing what the velocities and positions will be at ti plus h, okay? We know how to compute forces, right? And if we have just springs, you know how to do that. The mass matrix, it's just a diagonal matrix of all the particle masses. That's also super easy. The only problem is how to actually solve the system. And the idea of Baraff and Witkin was quite simple. They just, that's what's called semi-implicit integration. They just linearize the forces at the current state. Okay? So that's the key idea here. This F is the ugly nonlinear thing. And what they say, well, let's replace this ugly nonlinear thing but by its first order Taylor expansion. It's a multivariate thing, so again the multivariate calculus differentiation of function of multiple variables kicks in. And we write it like this. So these are the forces at the current step. That's where we currently are. This is the Jacobian of the forces, so the derivatives of the forces at the current step. These are derivatives of the velocities at the current step, so that would be our damping. This, by the way, this is what we already computed. Remember, when I was at the very first classes differentiating the potential of a spring, the first order derivatives, they were the forces, and the second order derivatives, the Hessian of the potential of the spring, that's the Jacobian of the forces. That's exactly this. So that's where it's useful, right here. This. Yeah, this is basically this is the step in positions. This is the step in velocities, and here you can also have time-dependent forces I never really used it myself. I'm not sure what people use it. In theory, the forces could vary in time. I guess you could like script. No, I cannot think of an example where there must be some cases where that would be useful. Usually this is not. Anybody has an idea?
What about damping?
Hmm?
What about damping of the force?
Well, damping is here. Those are velocity dependent force.
Stiffness of springs are functions of time.
Right. Like they're varying stiffness or something weird like that. Usually this would be just 0. But this might be not. The damping you can also set to 0, and usually that's okay. But this one you cannot ignore. This is the actual spring forces. This is the really important part there. I guess here I have another slide which explains what is what. So they are just Jacobians. Right, that this thing is typically 0. I guess you can ignore this exercise because we already done that. And okay, so what are we gonna do next, or what Baraff and Witkin are gonna do next? We are going to take this and plug it in here, okay? And so we can actually solve it, right? The first thing we are gonna do, we are gonna eliminate the positions. We are gonna write the system of equations only in terms of velocities v. Okay, so this is just a finite difference formula for the velocity. So we can do this, and we can use this formula to replace this with velocity. So we write this all in terms of velocities, and then we plug in the linearization of the force. Okay, that's what this is. Maybe with some simplifications. I don't want to do the math; that would be a mess. But if you want, you can just go through that, and it's not too much algebra to do. So this already is formula only in the velocities. And then what we need to do, we need to put these v, this is what we are computing, those are the unknowns. So we need to put them on the left hand side, okay? And multiply this by the mass matrix too. So that's what we get after we rearrange this, we get this. And the nice thing is that on the right hand side, we have terms that are known. We have a matrix here, which is also known. The matrix is the mass matrix, the Jacobian of the damping forces, the Jacobian of the position-dependent forces, the spring the Hooke's law. And here is the unknown. Here are the velocities in the next time step. That's what we need to solve for. Okay? Because once we know the velocities in the next time step, it's easy to compute the positions, right? That's just this formula. Once we know this, we just multiply by h, add to the previous positions, we have the next positions. So that's how Baraff-Witkin's method works. Okay? The only missing part, well, I guess the two, the two tricky parts there are first assembling this matrix, because you better get these derivatives right. So again, that's why we did it at the first classes, computing the derivatives. So here, this is actually the second derivative of the potential, or first derivative of the force, right? Remember what this was for the spring? This was these 3x3 blocks of the Hessian. So that's exactly what goes into the A matrix. I guess I have a little slide of that. So that's part 1, to assemble that matrix, and part 2 is actually solve the system of linear equations. And once you have done that, you have a beautiful integrator that works really well even for large time steps. I think the title of Baraff and Witkin's paper was Large Steps in Cloth Simulation. You were originally writing a paper on small steps in time integration with Tintin, but then it turned into the fast mass springs paper, which maybe I will tell you about later. That's essentially a different way to solve implicit Euler than Newton's method. That's actually an easier way, I would say, but it's like a recent research. So I will first discuss the standard things, and then we'll go into these more exotic topics, even though I think very useful. So that's how you assemble the matrix. So that's one of the tricky parts there. So you need to compute the derivatives right. So I guess the most important thing you need to realize about the matrix A is that it's very sparse. Okay. Everybody when you write it for the first time, you just use dense matrix routines. I always see some students use dense matrices and they're like, oh, that's so slow. It's slow if you use dense matrices. You have to exploit the structure already for like fairly small meshes. Okay, because what are the blocks? So we talked about this, right? How to compute the Hessian of a mass spring system, of the potential of a mass spring system, right? And there were these blocks. How could I? So there's a matrix like this, and there were these symmetric blocks like this, and I think if I remember correctly, it was even like A minus A minus A. Oh, A is already this, so let me call this, I don't know, B like block, B minus BB. Okay, and one of them was on the diagonal, and the other one was off diagonal, and the off diagonal elements were only for the connections. If one particle is connected to another particle, so if this is I and this is J, the block is there only if the two nodes are connected by a spring. Okay? So that tells you why the matrix is super sparse, right? Because probably your mass spring system will not be every mass point connected to every other mass point, right? That would be quite insane. More likely you have some type of mesh type structure where actually the number of edges is linear with respect to the number of vertices, right? So that's why this matrix is super sparse. It's also symmetric. Then we also discussed that. Hessian is always symmetric because the order of partial differentiation doesn't matter. So the Hessian is always symmetric, which is nice, which simplifies the solvers. But unfortunately, is it positive semi-definite? The Hessian? That would be the nice thing, right? That the best solvers actually even nicer would be positive definite. Symmetric positive definite, there you have that means you are in luck in terms of numerical solutions. That's the problem. It's not. It actually can be indefinite. That's exactly the consequence of non-convexity. That's why I showed you the counterexample the last time. Physically, it corresponds to the buckling instability, right? I showed this example when there are two springs which are compressed, but happen to be in the same line. That's a case where you have you will have some negative eigenvalues of the Hessian, and that's where some simpler solvers might fail. Okay, so how do we solve this? So let's assume we got a nice sparse symmetric matrix. Oh, one thing you should always do when you have a sparse matrix, make sure it really is sparse, please. Because the routines for solving sparse systems, they typically only take the upper triangle part. So if it's not sparse, and trust me, we learned the hard way, if it's not sparse, you will not know, you will just get the wrong result. It's just like a general programming remark. So okay, how do we solve the system of linear equations? And remember, we need to exploit sparsity. If you don't exploit sparsity, it will just be insanely slow. What do I mean by insanely? What is the cost of solving a system of linear equations if it's dense? If A is n by n matrix, what's the asymptotic cost for solving that? N cubed, right? What do you think the cost can go down to if the system is sparse? In our case, so by sparse, I mean there is only a linear number of non-zeros. So the matrix, if A is n by n, there is only O(n) non-zeros and non-zero entries. And that's what you will get in a typical mass spring system. Yes, yes. It can go, the complexity of solving a linear system, if it's sparse like this, it can be just linear. It's not easy to write such a solver, but it's possible. The trick is to use sparse Cholesky decomposition, which actually here is not a greatest idea because it will fail if your A is indefinite. So maybe you want to use LU decomposition or some regularization. That's a bit of a headache actually with Newton's method. Do you know how Baraff and Witkin solved this headache with the indefinite matrices? They did one very clever thing. They of course also run into that problem. What they did, they introduced adaptive change of the time step. if they got an indefinite matrix, they said, well, screw that and lower the time step h. Okay, and why that works is because this m here acts essentially as a regularization term. The m is a positive definite, of course, unless your masses are 0, but that would be weird. It's a positive definite matrix. So it acts there as a regularization. So if you bring h lower, you make this ugly potentially indefinite term smaller, and the system eventually will get positive definite. So that was Baraff and Witkin's trick. Or you can just use a solver which is robust to that. You can use LDLT decomposition. Does LDLT do indefinite matrices? I don't remember. But there are certainly solvers that can handle that. The other way you can handle it is just pass it to Cholesky. And if it tells you, sorry, I can't do it, it's not positive definite, then you can introduce regularization term. Regularization means just add some multiple of an identity, and you can be increasing this alpha progressively until you give it a matrix that it can actually factorize. Some people do it that way. That works reasonably well. So here you sort of don't have to bother about the detail because you don't want to be programming your own sparse Cholesky solver unless that's what you want to do for a living. Because there are some very good libraries that will do that for you. If you want to do sparse direct solvers, you want to use IGAN or Colmot or what else is there? There's Pardizo, which is in Intel MKL. You'll just get some library which does this for you. Because this is a whole industry. Because it's not easy. You have to, well, okay, I don't want to go into the details what all steps are there in a sparse direct solver. There is reordering to eliminate fill-in. There is the factorization itself, and there are tricks to make it parallel, and so on. The bottom line is you don't want to be programming it by yourself. So the advantage of the sparse direct solver, if it's a quality sparse direct solver, it will really be linear. And that's really nice. That will be really fast. The disadvantage is it also needs quite a bit of memory. It's also typically linear, but with some largish constant, like 10n memory or something like that. So for larger systems, it gets a little bit annoying because you know that the more memory you use, the slower it is, right? Because fast memory is only limited on caches. If you go to larger memory, you will pay for it by waiting. So that's a slight disadvantage of the sparse solvers. But the sparse solvers, they got really good recently, in particular because lots of people invested lots of time in it because it's a very, very general thing, right? You are solving linear systems everywhere, not just in physics. So these libraries do a very good job at it. Nevertheless, there is an alternative. You can use iterative methods. There are some pros and cons of iterative methods. Those are I guess the big advantages. This is stuff you can easily code up by yourselves. Even conjugate gradients, even though the math is a little bit tricky, takes a little bit to fully understand it. I would have to spend like a whole lecture on that if I wanted to explain it properly. But to code it, it's not very complicated. It's relatively easy. Jacobi and Gauss-Seidel, you do you know that? Yeah, that's even easier to code up, but the convergence is not so great. And the danger is that you get bored and you don't run it until convergence. And in that case, Newton is not really guaranteed to work properly because you don't really compute the right direction with Newton. You basically don't solve, if you don't solve the system properly, then all bets are off. It might work, it doesn't have to. So conjugate gradients is essentially like Jacobi Gauss-Seidel on steroids. That's my high-level explanation of that. That's what Baraff and Witkin used in their paper. Since then, I think the landscape has changed a little bit, and the sparse direct solvers got much better. So now I would really recommend you to use some of the sparse direct solvers, especially as they are quite easy to use in open source libraries like IGAN. That's what we were using, and it worked quite nicely. There is even, you can go even further. Some people like Eftichias, my friend from Wisconsin, loves that. Multigrid methods. which is another really cool thing that can also get the complexity to linear, but it gets really tricky, it gets complicated, and there are some tricky parameters you have to choose carefully, otherwise the performance won't be so great. Now the huge advantage of multigrid is that it parallelizes better than the sparse direct solvers. So if you are on some crazy GPU or something, then multigrid is something you should seriously consider. I guess that would be another bullet here, multigrid. Okay, so I can conclude Baraff-Witkin's method. So when you try this, you will find that this works really well, because you can take large time steps and it won't be exploding, which is a big relief from the previously explosive simulations. There are some smaller trade-offs. The stability is not really guaranteed, especially if you are using just the semi-implicit variant. I guess you can guarantee it by decreasing the time step. And here it's actually much better than decreasing the time step than in explicit methods, because here you don't have to decrease it so crazy as in explicit methods. And where is this? Yeah. Oh, yeah, and there is this problem. There is what is called artificial damping. The implicit Euler time integration essentially has the opposite problem of explicit Euler. Explicit Euler could be overshooting, and the overshooting can be explained as injecting energy into your system, right? And that's why it eventually explodes, right? So it actually, nature is energy conserving, right? If you have an isolated system, it certainly cannot explode by itself, right? It would be even better than perpetuum mobile. The implicit integrators, especially the first order variant, the implicit Euler, by the way, they are also higher order implicit integrators. There's implicit Newmark and implicit, I don't know how they are called, but they are higher order implicit integrators too. Actually, some people like to use them in a phase space. All of them, and especially the first order, the implicit Euler, have the problem that they actually dissipate energy from the system. So that's called artificial damping. So especially with larger time steps, you can observe it, that even if you don't have any damping in the system, the motion will actually be slowing down. If you like run a curtain simulation or something like this, if you, in theory, without the presence of any external forces, it should just be moving indefinitely, right? Like oscillating indefinitely if you let something swing. The implicit Euler won't actually do that, because the error, because there is still a numerical error. It's way better than the explosion, because instead of exploding, the energy is decreasing and eventually it will stop. So usually that's not a big deal in phase space, because usually you are injecting some energy into the system, like by the user dragging it along and exciting the system by himself or herself. But if you want to improve that, you can move to higher order implicit integrator, or again lower the time step. That will help with numerical dissipation. Oh, there was also some recent Stanford paper that was doing some tricks on energy budgeting, was essentially carefully reintroducing energy into the system to avoid this numerical dissipation problem. But again, in a phase-based, it doesn't really matter that much. I think it would matter more in like scientific computing, when you really want to simulate something. Correctly question?
Yeah, has anyone ever tried averaging the explicit and the implicit?
Exactly. I even have a slide on this. I didn't want to go into too much detail, but since you asked, this is very cool. And this is subject to some recent research. That's essentially what leads to what's called symplectic Euler, and it's pretty cool. The idea is that you go, what do? You go explicit on velocity and implicit on position. So you really mix the two in a funny way. And you get what's called a symplectic integrator. I guess it's an advanced topic. I would still say this is still a subject to research currently. We play with it some, and we did some work, some research with Tintin. And we actually found that it's not super stable, that this stuff can be quite easily explosive. But in theory, it has beautiful properties. In theory, this is exactly the right balance between implicit and explicit. It's something that almost conserves energy. That's the funny bit. What it really conserves is some symplectic form, which I'm not sure what that is. You need to go to some Caltech people who are researching this. They will explain you exactly what that stuff is. But yeah, that's very cool. It's essentially a blend of implicit and explicit integrators. We played with it some and we didn't get that great results. So I think there might still be something that needs to be discovered. That's my that's my current feeling about that. Okay.
It's interesting that why would you choose different velocity versus position?
Yeah. I mean, yeah, it's
really about the energy.
There's a paper you can read about this from some Caltech people. Ari Stern is the first author. I can look that up. It's you need to look at the phase space diagram, and it's preserving the symplectic form, which is something like the dot product between the change of position and velocity, something weird like that. You are really looking at the position and velocities together, figure out something about the geometry of the system. There should be some invariance due to the laws of physics, and it's trying to preserve them, but I'm really just like trying to fake my way out of it. It's cool stuff though, so if you want to look into something, this is a good topic for future research in physics, I think. All right, any other questions? I think we can keep it there, because I don't know it anyway. So well. Okay, so thank you.